I think this is working now. There we go. We're on Zoom. All right, the good news is we have internet again, so we can actually, do the lab. And today we're going to start the Armlab. I posted the teams, and now not everyone, as of the time I made the teams last night, filled out the student survey. So who still hasn't filled out the student survey? Okay, a few of you. Please do that. Basically, what will happen is if you haven't been assigned a team because you didn't fill out the student survey, I will find you a team when you come to lab today, and we'll stick you on the right team. All right. Yeah. So I don't know why I have an echo. Is someone's laptop on Zoom or something? All right. I think it's all right. It's not feeding back or anything. And that's off. So classroom and oh, am I not muted? There you go. My laptop was not muted. Is that better? Chat. Yeah, okay, great. Cool. All right, so we're gonna start the Armlab, and so we're gonna start with a basic introduction to manipulation. Now, right, we've all seen these robots, and each and every one of these you can think of as a manipulator, right? You have a classic industrial robot, which is a linear chain of actuators that rotate. You have, sort of mobile robots, but they might have robot arms on them, a chain of joints that allows you to move around and manipulate. And then you can even think of a walking robot as a series of manipulators, right? Each leg is its own manipulator. Each arm is its own manipulator. And then you can also think of these parallel mechanisms as manipulators. This Stewart platform allows you to move a flight simulator in 6 degrees of freedom so that you can train pilots to feel the sort of things they would feel when their airplanes are doing certain things. So they develop, reflexes that allow them to keep us safe as they fly. And then also use things like a delta arm, which is a very common manipulator you would find in a factory that is able to pick things up and place them these are able to move very, very quickly and also have 3 degrees of freedom so they can move things in space. So there's a common language for all these manipulators. And so we need to first talk about the joints. There's 2 basic types of joints you have in a manipulator, right? You can have a mechanism that can rotate, or a revolute joint, and you have a mechanism that can linearly translate, and we call this a prismatic joint. And then you can compose other types of joints from these 2 basic joints, right? If you have a revolute joint and a prismatic joint, you can make a helical joint where this rotates but also translates as it moves. And then you can compose from revolute joints, universal joints, which are able to rotate in 2 degrees of freedom, a spherical joint, which can rotate in 3 degrees of freedom, or a cylindrical joint, which can translate along one axis, but also rotate. So it also has 2 degrees of freedom, a translational degree of freedom and a rotational degree of freedom. Let me try to pin this so that students don't show up in the thing. All right, I might try to make this a little bigger so it shows up better on the YouTube. All right, so a degree of freedom, we often talk about all these manipulators having some number of degrees of freedom. And a degree of freedom is basically if we can minimally specify the parameters of this, right? But it will have, if the manipulator can be minimally specified by n parameters that will have n degrees of freedom. So if we talk about a rigid body on a plane, like a mobile robot driving on the floor, right? We can have its position, or me, right? I can move to an XY location in this room, right? We might have some origin, some global frame that maybe it's the corner of this room, and then I can specify my location in X and Y, and then I can also specify my orientation, right? Which direction I'm pointing, what my heading is. That is 3 degrees of freedom on the plane. For an object in space, like my phone, I'm actually able to position it, right, in height too, so that adds an additional degree of freedom, right? And then I'm able to rotate around 3 different axes, right? Often we like to think of this as pitch, roll, and yaw. That sort of comes from doing airplanes. But there's actually lots of different ways you can specify what the orientation is. And all of the ways have 3 degrees of freedom, right? There's a rotation around each of those axes in space. So any object in space will have 6 degrees of freedom, 3 for position and 3 for orientation, all right? And so the number of degrees of freedom of a manipulator, right, is basically equal to how it's able to position its end effector in the configuration space. Okay. And then, so each joint on the manipulator will add another dimension to this configuration space. So you can have more than 6 degrees of freedom. You can have manipulators with 7, 8, 9 degrees of freedom. And once you get above that 6 degrees of freedom, right, because we can specify the position and orientation of an object with 6, once you get above 6, you have what's called a kinematically redundant manipulator. That is, 2 of those degrees of freedom will control the same motion in configuration space or more, okay? And so you can have these redundant degrees of freedom. All right, and so the human arm has redundant degrees of freedom. It's actually more than 6 degrees of freedom. So we have a shoulder, right, with 1, 2, 3 degrees of freedom. It's basically a spherical joint, okay? We can rotate and translate. We have an elbow with 1 degree of freedom, right? So that's 4 degrees of freedom. And then our wrist is also a spherical joint, right? It can rotate, it can rotate this way, and it can rotate that way. And so we have 7 degrees of freedom of our arm. We have a kinematically redundant manipulator on each arm, okay? And so we're actually able to choose how we move, how we produce the same motion, right? I can rotate something this way, or I can also, rotate by rotating my shoulder or something like that. Plus, in addition to that, we have the degrees of freedom that our body gives, right? So I can move my body, I can move the base frame around by moving my legs, by moving my waist, that sort of thing, okay? So we are fully kinematically redundant, okay? And so once you know the degrees of freedom and the configuration space, you can define out what the workspace of the manipulator is. That is, all of the points where the end effector is able to reach, all right? And then there's 2 types of workspace. There's the reachable workspace, right? We can reach a point, but we might not be able to manipulate an object there, right? We can't reach an arbitrary orientation at that point. And then we would have the dexterous workspace. That is, all of the space where we can reach points with an arbitrary orientation. That's the workspace that we're able to actually do work in. Once we get out of that dexterous workspace, we might be able to do things, but we won't be able to do all of the things, right? It's reachable, but not dexterous. All right, so here's some common arms. And so once you stack up revolute or prismatic joints, you can sort of design a bunch of different styles of arms. So very common robot is the articulated robot. And it's basically, if you just look at the sort of the base, right, ignoring what happens at the wrist and the gripper, we have 3 degrees of freedom that allow us to position our wrist anywhere in space, right? And then typically your wrist would have 3 additional degrees of freedom that will allow you to orient it the end effector anywhere in space. So 3 revolute joints, the body, the shoulder, and the forearm. We can make, that's the articulated robot. We can make a spherical robot by replacing that last degree of freedom with a prismatic joint. So here you have a degree, 2 rotational degrees of freedom and a translational degree of freedom. And just like in polar coordinates, where you would specify a point based on 2 angles, right, and a radius. Similarly, we can change the orientation of that prismatic joint. We can make what's called a SCARA robot. All right, and these are very common in pick and place operations because they can be very fast. And you sort of use one joint for picking and putting down, and then the other 2 joints allow you to specify an XY location that you're going to do this picking or placing operation, right? So the same RRP series of joints, right, configured differently. This is also RRP, it's a revolute and prismatic joint. Configured differently can have a different workspace. All right, cylindrical robot, right? Just like in cylindrical coordinates where you have a rotational degree of freedom and 2 translational degrees of freedom, it gives you a shape of your workspace that looks like a cylinder. And then finally, Cartesian robots like these milling machines or your 3D printer, they have degrees of freedom that match the Cartesian coordinates, X, Y, and Z. So you're able to move basically in nice straight lines easily, right? It's harder to get a robot like that to move its end effector in a perfectly straight line, right? You have to do a lot of math to be able to do that. It's a lot easier and requires very little math to get the robot with all prismatic joints to move its end effector in a perfectly straight line. All right. And then we also have what are becoming very, very common these days are these collaborative robots, where you basically have a series of rotational joints and you might have many more than 6 degrees of freedom. And so what really makes a collaborative robot is not necessarily how the joints are arranged, although this is very common to have basically pairs of orthogonal rotational degrees of freedom. But really is that the joints tend to have sensors that allow the robot to detect when forces are outside of what they would expect for moving, like it hits someone and the forces go up because it's hitting an obstacle, and that way it can stop and correct and not harm the person that it's working with. So it's allowed to be collaborative. Most of the industrial arms, right, they're sort of fenced off within work cells and factories. Humans don't go in there while it's running because it's dangerous, because they have no sensors to tell when the robot is doing something very bad to the human operator that's in there with the robot. All right. And so all of these arms, or most of these arms, you can stick what's called a spherical wrist on the end. And this allows you to basically decouple kinematically the positioning, which is handled by the first 3 degrees of freedom, from the orientation. So if you have an articulated arm such as this, you can position the wrist at a certain XYZ location using these 3 degrees of freedom. And then you're allowed to position the end effector, which is the point at the end, right? The orientation of the end effector with these additional 3 degrees of freedom. So you get the 6 degrees of freedom that allows you to position and orient whatever tool you have at the end anywhere in space. All right, so how do these motors work? Well, they're invariably servo motors. Now, you can have open loop motors. People do try to make robot arms with stepper motors. There are problems with that. But usually you want to know where your arm is, so you want the feedback. So a servo motor is basically just a motor, right, with maybe some gearbox to translate rotational speed to higher torque, okay? So you move faster, you go through a gearbox, you get more torque, but you move slower. You're trading speed for torque. And then on the output shaft, where you're actually moving something, you have some sort of position sensor that feeds back into some controller, right? And then tells the motor to minimize the error between the angle that you want to be at and whatever angle that you're at. So a servo motor is basically just this. It has a gearbox, a motor, a DC motor, that's this part here. It has a gearbox, that's this part here, and an output shaft. And then on the back of the output shaft, this is it flipped upside down. Here we have actually this planar magnet that we're using as the encoder. And there's a chip on the top there that senses the orientation of that magnetic field, right? And gives you the position of this output shaft with a resolution, I think, is 4,096 possible positions. So it's able to do, yeah, there's where I think the resolution is 10 bits, so 4096 or 12 bit. All right. And then to run the controller, there's a microprocessor here that is running that control loop that's taking in the data from the feedback from the sensor that's reading the position of this magnet and driving the motor. And there's a motor driver here and two big MOSFETs that are powering that, that are sending current through that motor to drive it to one position or the other. In this case, the processor also handles serial communication. And when we want to tell this motor where to be, we actually just open up a serial communication link and transmit its desired position and then receive back all sorts of information from the motor. So the three motors, well, really two motors we're going to be using in this lab are this Dynamixel XL430 and this Dynamixel XM430. And these form the basis of the joints in the arm that we're going to use for this class. All right. These smaller ones cost about $50. They have a plastic housing. They have a lot less torque, right? And they move a little bit faster. For this motor, in our arm, the base is actuated by this motor, so the rotational base, because there's not very many forces on that. And then the wrist motors are this, because now we don't have to have much force. All of the other motors for the arm we're going to use for the Armlab are the higher torque XM motors. So these, actually, we have two motors on the shoulder, because that's where we need the most torque, right? That's carrying the most weight, because it has to support the entirety of the rest of the arm on the weight of all the linkages and motors down the serial chain. And then the elbow is also one of these motors. So I think the base, elbow, and then one of the wrist motors we've replaced with an XM430, because back when we did this first time, when we got these new arms, students would accidentally, it was during the pandemic, right? And so they couldn't be there with the arms. We had to use the arms remotely, and you could see what the arm was doing through a little webcam. But if the arm got into a mode that it got stuck and it had to be reset, students would have to reset it remotely and lose power to the arm, and the arm would just fall flat on the table. And we found that very, very quickly, the arms would destroy their wrist joints by crashing into the table. And so we replaced them with the higher torque metal motors, and that seems to have fixed the problem. All right, so to control its position, we're running this controller internal to the motor. It's looking at the desired position as a command that you send it. It's looking at the actual position of the motor from some sensor, and then it's running a PID loop inside to determine how to drive that motor to minimize that error. Now you have access in this lab or in the arm to adjust the gains of these controllers. They're initially adjusted by, they're initially set to reasonable values by the factory, and it's mostly just a proportional controller. If you find that you want to dive deep and tune the gains for better performance of your arm, you are allowed to do that. I will say that adding integral gain to your shoulder and elbow motors is a very bad idea, and will cause the robot to fail. So don't do that. It will saturate the motors and then they'll overload and then the robot will just fall. All right. So when you control these motors, you're setting the position that you want the servo to be at, but then you can also set a max speed to move and also a torque limit. And so basically it's sort of a cascade. It will move to a position at a speed determined by the controller, by the proportional controller, until it hits your maximum speed limit, right? And then it will only move at the maximum speed. Now, if you also have a torque limit, it will move at that speed until it hits that torque limit, and then it will only move at a speed where the torque is at the limit, all right? So there's, you're sort of setting the position. When you set the position in this region, it's working linearly, but if you exceed either max speed or max torque, it's going to be nonlinear. All right, so inside these motors, there's we communicate to them with a serial interface. So you'll notice a little box at the back of the motor that we plug in with USB. That's doing the serial conversion to the Dynamixel serial bus, all right? So each motor has 2 ports, and then there's 3 pins on each side. They're basically in parallel. You have a ground and power to send power to the motor, and then you have a single line that's sending all of the data, and it's multiplexing the data. This is something called half duplex. So the transmit, that is from the computer that you're running to the motors, and the receive, that is for the motors communicating to you, to the computer, all happen on the same line. And so it needs a special protocol for handling who is talking on the data line, okay? That data line is an asynchronous serial interface. So you need to communicate on it at a fixed baud rate. If you change that baud rate, the motors will not be able to understand what you're saying, okay? So this is, usually you would learn about asynchronous serial communication and baud rates in some EE class. There's not really much to know, but it is to know that basically each motor will have a baud rate. It's all the same baud rate. We set it at 1 megabit per second. And so when you're trying to configure the motors, you may need to set that baud rate. And if you're at a different baud rate, it's not going to communicate. So these messages have this huge packet structure. We send to the motor some command, right? And it has some header, and then it'll match on the ID. So each motor has an ID, and if it matches on the ID, then the motor knows you're talking to it, all right? And then it will read the rest of the data that's in your message. If that instruction is one that required the motor to then send a response, then the motor will take control of the bus and send a status message like this, right? Same header, the packet ID, and it will give basically what happened, all the parameters that you requested it return, and then a checksum for error correction. Right, so you're sending these packets, these large packets, back and forth between the motors, and you can do things like tell it what position to go to. You can do things like set the maximum speed, set the maximum torque. You can read back what position are you at. You can read back what speed are you moving. You can send a command to set the proportional gain or the integral gain or the derivative gain for your controller. There's all sorts of registers in these motors and commands you can send, all right? And the information is on the ROB550F website. That's the manufacturer of the motors. But you can also fire up this Dynamixel Wizard 2.0, which is on all the computers. And you can scan for all of the motors that are on the serial bus. In this case, 5 motors have shown up, and they are actually have different baud rates. On ours, they should all have the same baud rate. And then you can see all of the parameters that you're able to set. Some of these parameters are read-only. Some of these parameters you can only set when the torque is off. Other ones you're able to set. So you can read the, let's see, you can set a bunch of these. These are all things you can set, sorry. Down here below this, in this long list of parameters, there's ones that you can only read. So I suggest, if you're exploring how the arm works and how the motors work, you plug in the arm to your computer and you fire up Dynamixel Wizard. You scan for all the motors. You'll see them on the side, and then you can look at what the settings are and see what you can change. All right, and so this is our arm. And this is what we're going to be playing with. So we have 7 Dynamixel servos. Like I said, the base is an XL, and the wrist, 2 wrist motors are XLs. And then these are the higher torque XMs on the shoulder, the elbow, and the first wrist, the wrist joint. All right, it has 5 degrees of freedom. So it's actually not able to fully position itself in space. But for the task we're doing, it has sufficient degrees of freedom. We don't necessarily need to be able to position it anywhere in space. It can reach about 55 centimeters, and its accuracy, according to the manufacturer, and I don't believe them, is plus or minus 2.5 millimeters, okay? Basically, there's a difference between accuracy in the sense of you can reproduce a motion, right? But you actually didn't care where the end effector was. And accuracy in the sense that I'm telling this end effector to be at this position, and what is the error between that position and what I asked it to be at. All right. So this arm for this term, we've gotten working the newer ROS2 driver for the arm, and so we'll be using ROS2 for this lab. And so basically all the communication that you're going to do with this arm is handled already with this driver. And then they provide a Python interface for doing position control, so that you can call a Python function, set joints, right? And you can tell the arm where to set the joints. And so when we write code, what you'll be doing is calling on this Python library to control the arm. In addition, in this lab, we're going to have a depth camera. So a depth camera is a special sort of camera. There's multiple ways to build them, and we'll actually cover more in depth later how these all work. But basically, what you have is an image, like a standard RGB image that you would see from a normal camera. And then you have another grayscale image where the pixels represent how far away the points in space are from the camera, okay? And so in this case, as the pixels get further away, they get brighter. So the blocks that are taller here are darker, and then they get down. This image is actually from a Microsoft Kinect version 1.0. And not the one we're using, but it basically works very similarly or it produces very similar results in terms of producing a RGB image and a depth image, all right? The sensor we're using is a RealSense LiDAR camera, L515. They unfortunately discontinued it, Intel discontinued it, but it is quite nice. It has actually a LiDAR in it, a solid state LiDAR in it, that scans the environment using a time of flight sensor and gives you readings how far away pixels are from the camera. In the older sort of stereo camera style, or actually the Kinect worked by measuring the distortion of a fixed pattern, an IR pattern it projected on the world, and then it measured the distortion of that pattern, and then figured out what the depth was to the pixels. There's a few other ways to make a depth image. You don't have to do a direct time of flight measurement. You can actually infer what the depth is from either stereo discrepancy or distortion of a pattern. But we'll cover that in a few days or a few lectures. Yeah, that's the camera. All right, so for Armlab, what we're going to be doing is you are going to do kinematics, and we'll cover kinematics in lecture for the next few lectures. But kinematics is basically the question, can I find the pose where my arm is, given the angles, if I know where my joints are set, can I find where the end effector is? That's forward kinematics. And then there's inverse kinematics, is the question, if I want to be at a specific point in orientation in space, what do I set my joint angles to be, okay? And so mapping, going back and finding a map between joint angles or configuration space and the position in the workspace, position orientation in the workspace or pose, that is kinematics. And so you'll program up all the kinematics, we'll cover all the math for doing it, and you'll program up all the kinematics for the arm. We will also be doing trajectory following in configuration space. So if you want to move from one pose to another, and you know the joint angles, you can then make a trajectory to follow, to get the arm to move through different poses. And we will be doing this in configuration space. You can also do trajectory in the workspace, right? Follow this line or follow the curve of this surface. If you're building a welding robot, follow the curve of the metal so that you can weld along this precise path, all right? In this case, we're just going to be doing it in configuration space. Then we will be doing a lot of computer vision. So we will be using the RGB image from our camera, and we'll be using the depth image from our camera, and then we'll be using OpenCV to then figure out what blocks we're looking at, to differentiate between the red blocks and the blue blocks and the green blocks, to differentiate between the large blocks and the small blocks, to figure out if I have a stack of blocks, where is the top block in the stack? So I can pick it up and maybe take it off the stack, or if I want to put something on the stack, I can pick up a block and then put it on the stack. That we're going to be doing, that's all computer vision. All right, and then we'll be doing trajectory planning. So how we decide to move the arm to produce a larger effect or to do a task, okay? So in this case, how do we move the arm so that we can stack blocks up 13 high or something like that, okay? And so those are what we're going to be covering in this lab. All right, so I'm going to give you an introduction to the code and ROS in general. So how many people have used ROS? Okay, how many people have used ROS 2? Okay, fewer. They're basically the same thing. They just changed the names of stuff, but that's fine. So what is ROS? ROS stands for Robot Operating System, but it is not a traditional operating system, right? It's not the same thing as Linux, Windows, or Mac OS. It runs on top of some base operating system, and in this case, ROS 2 is able to run on top of Linux, Windows, and Mac OS. But in general, people focus on running it on Linux. Now, ROS provides client libraries. This is the big part of ROS, in the form of RCL, which is written in C, or RCL Pi, which is written in Python, or RCL CPP, which is for C++ code. And this is an API of functions that you can call to use ROS, all right? And then ROS is also a middleware layer. And in ROS2, the big change between ROS1 and ROS2 is this middleware layer was swapped out for a new middleware layer. So in ROS2, this is some data distribution system, DDS, and there's many, many versions of DDS that you can use, and you can use any of them with ROS. Basically, any DDS system that follows specific specifications can work. In the past, in ROS1, this was using TCP IP, which is the network code on your computer, right, for the protocol for connecting to the internet. And it has been changed out for this DDS system. ROS is also a set of applications and drivers. So I can go download a RealSense 2 ROS driver that will just communicate with my RealSense camera and produce messages that are compatible with ROS, right? And it is also a set of visualization and simulation tools. So it includes RViz, which is a visualization tool that lets me visualize the data in my system, and then Gazebo, which is a physics simulation tool that lets me simulate having a robot around, all right? So the architecture is like this. We're going to be writing at the application layer, right? We're going to be writing our own nodes, and those nodes call from the client layer. So we're including code from, in this case, RCL-Pi, which is the Python API, which calls on RCL, the C implementation. All right, and that lets us use ROS in our code. And then below that is the middleware layer that's doing all the communication between the sending data from different nodes in our system. And then that sits on top of whatever operating system we're running on. In this case, we're running on Linux. So there's a few concepts that we should cover in ROS. So the idea of a node, what messages are, topics, services, bags, and then you can read all the documentation there. We're using Humble Hawksbill for this lab. We used to use, but ROS releases a new release every year, basically. All right, so a node is a single unit of execution. Right? It's a single executable. It includes that client API that lets it be ROS. And the idea is that you would either have, a node could be a driver, it could be something that communicates with hardware and then publishes messages about what the hardware is. Maybe it's a sensor, what the sensor is reading. That node could be a visualization node. It receives messages and then formats them in a way to display them to the user. Maybe it shows you images or shows you the maps that it's creating or shows you the location of the robot. Or it can be an application that is taking in sensor data and producing maybe a state estimate or an estimate of the location of the robot. Maybe it produces an estimate of the location of all the blocks in the workspace or something like that. That would be an example of an application. And so these nodes communicate with each other through messages. And in ROS2, there used to be, in ROS1, there was a central master that coordinated all the messaging. Now it's there's no master. All the nodes can just talk to one another independently. There's no central marshaling. So the nodes communicate with messages. The messages work on a publish subscribe model. So if I'm, say, a sensor and I have a node that is my driver, say I'm a LiDAR sensor, I'm going to take a measurement and then I'm going to publish a message. The driver node is going to publish a message containing all the sensor data that I just took, all right? And then whoever else needs that data, wants to use that data, will subscribe to the topic that those messages are being published on. And then whenever a message is published on a topic, I will consume that message and then do something with it, all right? And so we're passing messages all around, all over the place between different nodes all the time. And it uses, in this case, ROS2 uses DDS as that transport layer. All right. So as an example, if I wanted to receive the joint positions from the arm, I have a driver that reads all of that continually reads from the dynamixel motors, communicates with the dynamixel motors and reads their positions, and then publishes their positions as a message. And it publishes it to a topic RX200/joint states. All right. And then my visualizer, maybe my control station, can then subscribe to those messages and decode those messages. And it knows that the messages are of type sensor messages joint state.message, right, which contains all of the angles that my joints are at. All right, so here, this is from the original ROS2 paper. All right, so you might have a node here, node, so node A is subscribing to some topic and getting the messages. And then there's also, in addition to messages, there are other types of messages. They're like messages. One is an action and one is a service. So a message is just a message. It's just data that gets sent on a topic. A service has a request and then a response. So you could, instead of sending messages with joint states, you could set it up where you requested the current joint states and the service would respond with whatever the current joint states are. We actually are not using any, we might be using a service for turning on and off the torque of the motor, but it's transparent to you. You don't have to worry about it. There's also something called an action, right? So with an action, you send a goal message, you receive a feedback message and a result message, right? And so it's basically just a way to structure the messages based on sort of what they are, whether you're doing an action, whether you're just monitoring a topic of data, or whether you have some service where you're requesting something to happen and then receiving a response. All right, and these are all on topics. Basically, you can just run ROS2 topic echo and see all the messages that are coming in on some topic. Okay. All right, so we'll be using RViz2. This is actually RViz1, but oh well. Just to visualize common messages. So it's able to visualize the joint positions, the configuration of the arm and where all the joints are. It's able to visualize the camera images. It could also visualize that you could turn that depth and RGB image into a point cloud and show that. Basically, any message that you're interested in that has visualizable information, you can visualize with RViz. If it's not a standard message, you might have to write your own plugin. We won't be doing that in the class. But our launch file will automatically launch RViz and a model of the robot arm, and will show the current position pose of the arm. All right. So if you want to know what's happening on a topic, there's a nice happy command called ROS2 topic. It used to be ROS topic and ROS1, but now everything is ROS2 and then topic. So if you want to see all of the active topics that all of your nodes are publishing on, you can run ROS2 topic list and it'll show all of the topics. If you want to read the messages that are on a topic, you can run ROS2 topic echo and give the name of the topic, and it will show you all of the messages as they're published on those topics. You can print information about a topic. You can actually print the type of message that's on a topic. If you don't know I want to read the data off this topic, but I don't know what that data looks like. You can figure out what type of message is being printed, right? By doing ROS2 topic type. And then you can find out the definition of that message so that you know how to decode it in your code. And then if you want to directly send data to a topic, you can actually do that from the command line. You don't need to write a little program to do it. You can just publish some data to a topic. You need to make sure that your message type and args are correct for that topic. ROS2 also has and ROS1 also has a sophisticated logging system called ROSBag. And so we can record all of the messages that happen while we're running our robot. Okay, cool. We're almost done. And then I can play them back. So I can run I can record them. It will save all of the messages and then what time they happened. And then I can play back everything that happened and it will replay everything, resend those messages when they were sent, which is great for debugging and doing simulation and working offline. So you're able to actually take your stuff home, record a bag of all the messages. You don't even need to be near the robot, and then you can develop using a log file. All right, so you can record your own logs, play back your own logs, and there's a set of tools for ROS called RQT, which are basically GUI tools written in Qt that let you do stuff. So in this case, RQT bag lets you play back and see all of the topics that were where messages were being published. And you can even edit, I believe, edit the log file there, remove messages or something. All right. So when we get to Armlab, everything we're going to be doing is going to be based in this control station. So this control station is a GUI that lets you control the arm, and you will be editing this to add functionality. So you'll notice there's a bunch of buttons on the side, user 2 through user 12. You will be adding functionality to these buttons and programming them. And there's buttons over there, task 1 through 5, for you to attach to the bits of your code that run the competition tasks for the end, okay? You can also move the sliders around to adjust the joints, and it has readouts of the joint coordinates, the end effector location, and the world coordinates and of where your mouse is. You'll be writing all of this stuff, but we'll give you the template for it. All right, it communicates with this Interbotics XS arm node, and that's what the driver for our robot. Time profiles. Okay, one thing about the node, the XS node, is when you tell a robot, when you tell the joint to move, you don't just tell it what position to go to. You set also a moving time and an acceleration time. So if I want to go from 0 radians to pi radians on my rope and my joint, I need to tell it how long I want to take to move to that new angle. And I also need to tell it how long to spend accelerating and decelerating. So accel time cannot be more than half of moving time, right? Because otherwise it doesn't work. If accel time is exactly half of moving time, you will spend half of your time accelerating and half of your time decelerating. But you can have accel time shorter. So if you limit it, if you have a longer accel time, it won't be so jerky. Obviously, setting the moving time is going to change how fast it's going to move. We have the RealSense 2 camera node. So this publishes RGB and depth images to the /camera/whatever topics. All right, and then we'll launch this with our launch file separately. So that will, once we launch, it will just start publishing images from the camera. You can, there's parameters actually in this launch script that you can adjust. And so we keep a local copy of this in the repository, and then you can copy it to the system and run it later, because it's actually stored globally. Like it's stored in /opt/share/ROS or whatever. And so If you are using the same computer as another group and they have a different configuration for this, they're going to copy it in. And then when you start, you're going to have to copy yours in because it only reads it from that one spot. Okay. Right. So basically, we have the control station. This is the software. We have a RealSense 2 node, an Interbotics node. We also have an April tag node, which I'm not showing here. And then your code is going to be running in this control station. Control station creates 3 threads. Now they're sort of not real threads because Python has a global lock, but a global thread lock. So it's only ever running one of these threads at a time, but it's useful for thinking about the execution to happen in different threads. Right? You have the camera code that's running a video thread that's doing that's reading in the images and doing all the computer vision stuff. You have the RxArm code that's running the ARM thread that's getting all of the joint information from the ARM and maybe sending joint information to the ARM, and then, or no, it's just reading in the joint states. And then we have a state machine code that's running the state machine thread that's sending commands to the joint and to the gripper in response to how the joint states are changing, okay? So these are the 3 bits of code that you're gonna be writing in and the 3 threads that you're gonna be writing. Okay, that's the same thing. Okay, so I will, since we're out of time, right? Yeah. I will talk about this in lab, but how to get started. Basically, you're going to start by forking the repo to your own space and installing the code, get the ARM moving, and then I'm going to expect you to sort of read through the code and understand. Generally, start reading through the code. It's quite a large code base, but not as large as BotLab. But to understand what's going on, okay? And then hopefully today you'll be able to write a very simple waypoint follower to get the ARM to go through a set of joint positions and do a little dance, all right? And then if you do that really quickly, you can work on your teach and repeat, where you tell the ARM, you move the ARM around physically, have it record positions, and then have it play back all those positions that you went through, all right? Thanks, everybody.